Okay. This is a picture of our experimental setup. We had a ramp, threw a ball down the ramp. We hit a stationary ball, and we used Audacity to determine how long it takes each ball to hit the wall. Okay. This ball is offset from the path of this ball. Now, implicitly, the ramp is set up along the y-axis. Don't forget the x-axis perpendicular, and the origin is right here. So this ball is a little to the left of the origin. This ball, if unimpeded, would pass through the origin. The center of the ball would pass through the origin. So you have a glancing collision. This ball goes off this way. This ball goes off this way. Mass of this ball is M1. Mass of this ball is M2. These distances from the y-axis to each wall, and each wall is parallel to the y-axis. I didn't do a good job of making that parallel, but there it is. Okay. This wall goes along the line x equals d2. This wall along the line x equals negative d1. So if we use v1j for the vector velocity of ball one just before collision, and if we assume that there's negligible energy loss, there's so little energy loss due to the rolling friction with the tabletop, that there's negligible difference in calculating the velocity. If you assume there's no energy loss, okay? The velocity would not change. The velocity is not going to be much different than what you get if you assume energy constant. No energy loss as the balls roll across the next line. Okay. Not an elastic, perfectly elastic collision, so there is energy loss, but not in the rolling balls. All right. If the time between collision and hitting this wall is T1, and the time between collision and hitting this wall with this ball is T2, and if we ignore the diameter of this ball and how much it's offset because we didn't really measure that. Okay, so that's one source of uncertainty in the experiment. We make the simplifying assumption that both balls started out at the origin, even though that's not really true. Okay, got to take the diameter of the balls into account and make some compensation for that, but we'll keep it simple. Okay, so the question is, time first ball to hit the right wall is T1, time required for the first ball to hit left wall is T2, and that's relative to the time of collision. Okay. And we're kind of implicitly assuming, which isn't the case, but assuming that the collision occurred in an instant. Has to be spread out because of the impulse momentum there. Shorter your time, the more force there is exerted during the time. And if the collision is instantaneous, then you need infinite force and the balls shatter and kill everybody in the classroom. Okay. Probably take out the rest of the world too. All right. So all that aside, simplifying assumptions, both balls start from the origin. And these times are measured from the instant of collision, and that there is an instant during which the collision takes place. What can we determine? Okay. And I made the claim, I think we can analyze the entire collision just from this much information. And that's information that you have in your Audacity files. Okay. Okay, so, well, I posed that question, immediately got a good answer. So, well, you can figure out the x velocity, the two balls. You know, the x displacement of this one is going to be It'd be D2 minus the radius of the ball, but we'll pretend the balls are small enough that that doesn't matter. And then if we want to compensate for that later, we can, okay? We know that this ball traveled in the X direction and got to the wall in approximate time T2. We don't care yet about what it did in the Y direction. We're going to be able to figure that out. And the second ball hit the left wall at time T2 after the collision. We can determine the velocities. Okay, so given information, I call these D1 and D2 because I was numbering from left to right. That's going to be a little confusing. So I'm going to call this D2 and I'm going to call this D1. Now I can say what I want to say, that U1X is D1 over D1. For U is the ball one velocity after collision. Okay. Don't need an arrow over this, it's just the X component. Although if we wanted the vector X component, we could do U1X times I. Okay, and U2X is negative D2 over T2. And we'll make a similar comment, that's pretty implicit. We know what U1X means, we can figure out what U2X means. Okay, do we agree? Okay, good. Now where can we go from there? Okay, now we'll just make a little statement here. Unchanged. PX total have to be unchanged. And TY total has to be unchanged in collision. Now, if PX total is unchanged, if your total momentum in the X direction, to just put it in words rather than symbols, because words can be easier to understand, or at least to clarify the symbols. Your total X momentum is unchanged. What's your total X momentum before collision? Well, R gotta go to the components and take a little. The looks in your pages. Let me write it on here. I mean, we know that momentum's unchanged. The impulses experienced by these balls are equal and opposite. And those impulses, the impulse of each ball is equal to the change in its momentum. And that's an idea you really want to incorporate. Now, there's our equation. So it's not an equation to memorize. It's just, okay, impulse momentum tells you that you have equal and opposite changes in momentum. So the total momentum before has to equal the total momentum after. You really need to understand that deeply, okay? And as you do problems, you understand it more deeply. So we have this equation for the x momentum. And we have the same equation for y. We just replace the x's by the y. We have the y components. In this case, what's a v1x? That's the velocity of the first ball, okay, before collision in the x direction. It's zero because it's moving purely in the y direction. So we have zero here and we have zero here because neither ball has any motion in the y direction. And then this is M1 and U1x is D1 over T1 plus M2 times negative D2 over DT2. I'll just put the negative out here. Okay. Now, what is it that you know and what is it that you don't know about that equation? Okay, so what's known and what's unknown? Well, the only things that are unknown are M1 and M2. We know everything else, or at least we'll be able to determine it. Now, in analyzing experiment, you're going to make the not precise assumption because we didn't go to a lot of trouble to make the two sides completely parallel, make sure that the ramp was right in the middle, but it was close. Okay. So in analyzing the lab, you're going to be able to get the ratio of the masses just from the time it takes each ball to get to the wall. Okay. At least for the trials in which you didn't have a pretty light ball here and this one hit over here, but if you know where it hit, you can still do the y momentum, right? You measure where the thing hit. Okay. So one or another. Okay, now if D1 and D2 are equal, let's just what's M2 over M1? Well, you add M2 D2 over T2 to both sides. And then divide by this side, you're going to get you're going to get D2 T1 over D1 T2. I think I've got those right. And rather than going back and writing out the steps here and being really careful, I'm just going to check it against common sense here in a minute. Okay. And actually, yeah, pretty sure that's right. Okay. It's easy to get them cross products and stuff mixed up. If D1 equals D2, then M2 over M1 is T1 over T2. And here's where we can apply a little bit of common sense. Okay. So, which ball would you expect to hit the wall first? The more or the less massive ball? Okay, so, intuitively, if one ball is much more massive than the other, like one of these is a bowling ball and the other is a BB, you're pretty sure that the BB is going to hit the wall before the bowling ball, right? Of course, you can't even fit a bowling ball in the apparatus we have, well, sort of diameter to throw things off. Okay, so that's what we expect intuitively. That's what the equation tells you. It tells you if M2 is bigger than M1, then T1 is bigger than T2. Okay, T1's a time. If M1's bigger, then if M2 is bigger, then M1 is at least less massive, and T1 is going to be bigger. Wait a minute. I'm getting myself confused. Okay, M2 is bigger, then T1, the time for the first ball to hit the wall, is going to be greater. Okay, is that clear? If M1 is bigger, then T2 is going to be bigger than M1 is bigger than M2, T2 is bigger than T1. The ball opposite, the more massive ball, is going to be the one that hits first. So everything so far is algebraically correct, I think. And I'm particularly confident that the algebra is right because it fits so well with intuition. Still, if I was being smart, I'd go back and, write out all the steps of the algebra and do it more carefully. All right. Well, that's pretty good. Now, what else is there to determine about the collision? Well, the after collision velocity, the velocities in the y direction, right? So we still have to find U1y and U3y. Now, can we do that? We have the information to do that. Okay, so suggestion I got was, well, can you just use M2 equals M1 T1 over T2? Okay, or maybe it was M1 equals M2 times T2 over T1, but either way, you can express all these masses in terms of one variable. That means we have one fewer variables. So how many variables do we have here? We got 1, 2, 3, 4, 5, 6. We don't count M1 and M2. Okay. So the equation originally had 6 variables. We know a lot of those quantities. Do we know enough? Okay. Well, we can eliminate one variable. Now we only need 5. Okay. Now what do we know? Do we know U1y? No. Do we know U2y? We don't know either of those. Okay. But do we know V1y? We know V2y? Yeah, that's just V1. It's all the velocities in one direction. That's just V2. Okay. So what's that going to allow us to determine? Well, we're down to one variable M1, and then U1y and U2y. That's 3 variables. And we only got one equation. So that means we need more information. Well, I think if there's anything else we could do. Okay, now I ask, is there anything else we can do? Okay, it's like you've got 3 variables here, okay? Well, it might not be obvious when it's written like this, but we take the information we have which is, of course, this ratio that we just talked about. And then we have V1Y equals just V1, which we know, and V2Y equals 0. Okay. We write out the equation. We just substitute into the equation. And then we write it out. We probably write just this out directly. But it doesn't hurt to write an intermediate step. And now we see that, okay, what don't we know? We don't know U1Y, we don't know U2Y, and we don't know M1. Okay. We'll kind of circle that. But of course, I got the suggestion. Somebody, when I wrote this out, somebody said, well, you just divide through by M1. Then you've only got two variables and you can find the ratio of U2Y to U1Y. Okay, makes sense? So go ahead and do that. Do the arithmetic. What's the ratio of the Y components of the velocities? Okay. Well, we divide through by M1, we get U1Y plus M1 T1 over T2 U2Y equals V1. So that, let's say, we'll do U2Y over U1Y. That's a little more complicated than before. But since we did M2 over M1, we'll do second over the first. And maybe I did something wrong here because we got a question. Yeah. I wouldn't have liked having this in there. Thank you. The M1 divides out, right? Okay, so we then have what? Write it out carefully. You're going to get P1 over T2 times U2Y equals V1 minus U1Y. And that's okay. Now I'm writing that kind of small. But we can solve this for U2Y. And we get this expression. And if I did my algebra correctly, then we conclude that U2Y over U1Y is this. So as I solve for U2Y, and then I divide that expression by U1Y. That makes sense? A little dubious. Well, let's see if it makes sense. Okay, so if I did that right, is it reduced down to something? matches our intuition. First place, we divide V1 by the U1Y minus divide the U negative U1Y by U1Y. And we get this expression. And I'm not all that happy with it. Hang on a second. Okay, now I actually expected to get something a little simpler than what it looks like we got. But I do need to move on to the stuff you're gonna have for homework before the next class meeting. The following chapter, okay? So right now, we're gonna leave it at this, but give it some thought. What we've illustrated, of course, is how we can start with a little bit of information and then move from one clue to another to assemble a lot more information. How we end up with this thing, and yeah, I'm being stupid this morning, but I'm not getting a simple ratio. Okay, and I'm not gonna worry about that. The whole point is here is the conservation of momentum for two particles in an isolated system. Here is the information you get from the X component of the momentum. Here's what you get from the Y component of the momentum. They're independent. This is independently true. This is independently true. X and Y directions are independent. Okay. I'm going to shift gears. I want to talk a little bit about rotation and rotational kinematics. There's something I want to demonstrate.